For today, our presentation, what we're going to be doing is I'm going to be giving you a presentation recap, talking about all the research that we've done up until this point. And as well as that, I'm going to be talking about the material takeoff list that I've created from each of our building models, telling how many beams and walls are in each one. And following me will be Nicole, who's going to give you her logistics analysis that she's done, talking about costs and shipping. And then after that, Jesse's going to be coming in and talking about his mill to site analysis. John then will be coming in and he's going to be talking about life cycle analysis and what exactly that is. And finally, Errol is going to be coming in and he's going to talk about the structural analysis program that he's been running in Robot. Gets here quicker. It's not going. Sorry about this. Seem to have some technical issues going on here. There we go. All right, so over the last few months, we've been looking at a new material called cross-laminated timber, otherwise known as CLT. What a CLT panel is, it's made up of dimension lumber, 2x-dimension lumber, whether that be 2x4s, 2x6s, or 2x8s. And what happens is that this dimension lumber is laid flat, and it's then each layer above that is orthogonal to one another, each layer being orthogonal to one another. And so if you know anything about plywood, it's going to be very similar to that, only this time instead of using veneer strips, we're now using dimension lumber. Or to further illustrate the point, if you have ever played the game Jenga, you get the picture. Each layer is oriented orthogonal to one another. And so this is the material we've been researching, and the idea is that this type of panel could possibly be replacing material properties such as concrete or steel, which are commonly used in the industry today. And so our ultimate goal for this project is to develop a supply chain as we can in timber and have a positive impact on our environment. Next, what you can see on the bottom graphic here is a picture of the market analysis that we briefly began. And what we saw here and what we wanted to find was just simply how many markets are going to be in the Pacific Northwest, and as well as how accessible are these different markets. Because the CLT is going to be moving to and from each market, we need to know what kind of railways and roadways are going to be going and entering into these markets. Otherwise, we won't be able to actually do the shipping that is needed to bring these CLT panels into the building site. From this point, we chose the city to base our building models in, which was Seattle. And what we found in Seattle is that there's been significant increase in the building and construction of multifamilies and offices in the last 30 years. It's important to note as well that warehouses are utilized a lot in Seattle. There's a lot of large companies here that will use these warehouses for the production of their goods. And what they do there is once their warehouses met their specifications of its lifetime, they'll wipe these out and just build brand new ones. So we wanted to model that as well. And so this is how we determine what kind of building models to build for our baseline models. Knowing this and knowing that we're going to be building in Seattle, what we found was that the zoning requirements and how each source defined their structure is all different. IBC, LEED, and Pacific Northwest Energy all gave different categorizations for what a building structure is defined as. IBC above 75 feet was a high-rise, where Pacific Northwest it was different, and then as well as LEED gave different categories, each one. And so what we as a team needed to do is find out what is going to be our baseline to define each structure, which leads me to my next slide. Excuse me, I'm in the way there. And this is how we defined our structures, and it's our baseline to move forward with. And what you can see here is that anything between 1 and 3 stories is categorized as a low rise, between 4 and 8 is a mid rise, and above 9 stories is now going to be a high rise building. And so now we can go in and we can build our structures according to this, which we have right here. We built 4 different models, a warehouse, which is in that 1 story low rise, a multifamily mid rise, which is between that 4 and 8 stories, and then we have the multifamily high rise and office that are both high rises, which are above 9 stories. And so what we wanted to do with this is get a volume count of how much CLT is actually going to be utilized in each one of these buildings. And furthermore, what we ended up doing is we designed the panels, the walls, and the floors accordingly to the loads that are going to be happening on them, just gravity, as we mentioned earlier in previous projects. And so from these design loads, what we did is we updated the models to be either 3-ply, 5-ply, 7-ply, or 9-ply. So that way we can actually get a materials takeoff list, which I have here for you. And this will further help us in the logistics that is going to be presented to you in just a moment. And so here you can see the amount of beams and the amount of walls that are needed for each building type, followed by what type of panel it's going to be, whether that be the 3-ply, 5, 7, or 9-ply. And so next, Nicole's going to come up and she's going to talk to you further more about these logistics.
So at this point, we have used CLT families in Revit to develop estimates for the size and approximate number of each of the CLT panels we're going to use. And so behind me, you can see here the different panel sizes that we're going to use. We're looking at lengths of 48 feet, 24 feet, and 16 feet, with widths of 8 feet and 6 feet. And so the challenge then becomes, how do we ship these various panel sizes? So to begin our exploration, we looked at 4 different options. We looked at a center beam rail car, a dry freight 5-axle truck, and a 5-axle flatbed truck, and finally a 3-axle flatbed truck. So to note out a couple specifics for the shipping capacities, dimensions, and weights for our freight, we have the center beam rail car is going to have a maximum length of 73 feet with a width between center beams of 4 feet and a maximum weight of 225,000 pounds. That 5-axle freight truck is going to have a maximum length of 53 feet with a width of 8.5 feet, a height of 8 feet, and a maximum weight of 48,000 pounds. The 5-axle flatbed is going to have the same dimensions and weight capacity, but it's going to go up to about 8.5 feet in height instead. That 3-axle flatbed is going to go down to a weight of 20,000 pounds, a length of 24 feet, and a height of only 6 feet. And so when determining further analysis, we have decided to eliminate that dry freight option. The 5-axle flatbed has the same dimensions and weight capacity, and it has the ability to cover our CLT during shipment, and the complications of loading that dry freight just didn't seem worth it when we had an equivalent model there. So our analysis will continue to explore the rail and 2 other truck options. So here we see the maximum length that each of these different shipping options can take. So the rail and that 5-axle truck can't hold that 48-foot panel. However, that 3-axle is only going to go up to that 24-foot panel. Notably, the rail here is only using 48 feet of its maximum 73-foot capacity. We can't quite fit 2 panels on there, so we have a lot of leftover room. This may not be the best length to be shipping on that option. Here we have the minimum panel length, so that's that 16-foot length, and we can fit 4 of those on the rail, 3 of those on the 5-axle truck, and again 1 on that 24-foot 3-axle truck. The rail now is using 64 feet of the available 73 feet, so we're getting a little more efficient, but not quite there. But that medium length really fits well on that rail. As you can see, we have 3 on the rail, we have 2 on the 5-axle truck, and 1 using the full length of the 3-axle truck. With that rail center beam car, we are now using 72 feet of the available 73 feet, so this seems a pretty efficient option on that rail. For the remainder of my presentation here, we will be using a 24-foot by 8-foot 5-ply panel to compare the shipping options between these 3. So whenever I refer to a panel or so many panels on these trucks, I am again referring to that 24-foot by 8-foot 5-ply panel. So going into shipping by volume alone, we can see that we can get 36 panels on the rail center beam car. Each of the boxes you see in that diagram is equivalent to 12 panels. And this option is limited by width. So between that center beam and the outer edge, we are only allowed 4 feet. We can get 2 4-foot sections on either side, but the volume capacity for this is limited by that width dimension. The 5-axle flatbed, as illustrated in the image, can support 28 panels. It's going to be limited by height. The 3-axle, as seen, can hold 10 panels. It too is going to be limited by height. But volume doesn't necessarily answer the whole story for us. And when we take a look at shipping capacity by weight, we can see right away in this image that the panels supported by the trucks have gone down. The rail center beam up here has gone up to 1 box in that rail is now equal to 19 panels, which is greater than the 12 we saw in the last image, which means our rail is actually limited by volume and not weight. However, the trucks, that's a different story, where before we could ship 28 panels on that 5-axle truck, we are now only able to ship 12 as seen as in the image. And with the 3-axle, we have gone from 10, we have gone down to 5, so we're losing about half our capacity when we take in those weight restrictions for the trucks. This leads us to an overall capacity for legal before we get into overhaul shipments. And so we're going to have by rail, we can ship 36 panels per load. And we can ship 12 panels on the 5-axle truck and 5 panels on that 3-axle truck. As an interesting comparison, after realizing how much weight restricted in the truck shipments, we decided to look at the comparison of shipping these 24-foot by 8-foot 5-ply CLT panels to an equivalent size panel in concrete. And as you can see in this image, where the yellow is the amount of CLT we can ship of this panel size, and where the gray on the bottom is the amount of concrete. So when we have 5 panels on that 3-axle truck, we're down to 1 concrete panel. And when we have 12 panels on that 5-axle truck, we got down to only 2 concrete panels. So we can ship more CLT than we can concrete. And this is just something interesting to keep in mind as we look at the shipping for these buildings. So here we have an interesting exploration for the office building and the large warehouse as far as exploring if each of these shipping options were to ship the entire building, how many loads would it take? And so it's important to note that for this analysis, we assume that 24-foot by 8-foot panel, and this is done assuming that each load is filled to its theoretical capacity. This is not quite accurate because obviously we're going to have different sized panels, different lengths, but this just gives us a good exploration of which shipping option seems more efficient right off the top. And so we can see that that rail-centered beam car is clearly more efficient, and that smaller 3-axle truck seems almost silly. And this is similar to, we're stuck again. Sorry. This is similar too for the residential buildings. We again have that trend where the rail center beam car is going to be less loads and that smaller 3-axle is going to be higher loads. We also realize that in reality we're going to be using combinations of these shipping options, and that 3-axle is best used in the smaller, tight city areas where we potentially may not be able to get that 5-axle flatbed to site. And so this is an interesting thing to keep in mind as we go on. But for now, we're going to have Jesse come forward, and he's going to go into more depth on shipping the office specifically and some of the supply chains available in Washington.
How's it going, everybody? So I'm going to explain to you some of our supply chain options that we are currently looking at. If you've followed us from the beginning, you've seen in our first 2 presentations some of these models, and basically what these supply chain models are saying are that we have all these different steps in order to convert our raw material, our trees, into CLT, and then this analysis will help us decide where we want to have these conversions take place. In presentation 1, we did a thorough analysis of the harvesting phase, and then in our most recent presentation we did a lot of our site construction analysis. So we're going to take a look at the stuff in the middle today. We're focusing on 4 ecoregions. These are our 4 different supply chains, and from west to east we're going to call them WA1, WA2, WA3, and WA4. This consists of the Coast Ranges ecoregion, the Western Cascades ecoregion, the Eastern Cascades ecoregion, and the Okanagan Highlands. So in order to effectively compare all of these supply chains, we're going to need to pick a common location for them all to end. We decided to use the South Lake Union area that we studied a lot in our previous presentation, especially this SM240 region down here, this kind of purple color. You'll see it also on the map up this way. The reason why we chose this zone is because it utilizes 2 of our baseline models, the large office and the multifamily high-rise. We can actually use them both in the same lot in this region. Another benefit of this location is that we have a lot of these SM85 regions as well. These zones can accommodate the mid-rise multifamily buildings. And yet another benefit is that we have our small warehouse analysis was done down here in this red region. And that's less than 5 miles away from the South Lake Union zone. This is also where all of our rail transfers will end up. There's a distribution yard there that will effectively move our material from rails to car or to truck, and then it will take I-5 up to the location. Now, if we zoom into this SM240 region, we can kind of see the specific site that I chose. It was 120 Westlake Avenue. I just picked kind of a random lot in the middle of this zone so we can get a good idea of how we're moving our stuff to it. You will notice that there is a building already there, but there's many sites that are in development currently. In fact, the one across the street is building the same sort of structures that we would like to build. So that's a very feasible location for us to end. You also notice that we have the WA 1 and WA 2 supply chains are going to end here. They're going to come from the north, and then WA 3 and WA 4 are going to come from the south, and they're all going to converge at this point here right off of I-5. And as Nicole said earlier, we aren't really going to utilize those smaller trucks. Our concern was that we wouldn't be able to navigate in this kind of downtown area with all the tight corners, but as you can see, no matter where we wind up in the SM240 region, all we're going to have to do is take a left turn on this kind of main road here, and that shouldn't be too hard for a semi-truck to do. So these are the options that Nicole showed us earlier. She explained why we can eliminate the dry freight and why we can eliminate the small flatbed she just discussed. So we're going to focus strictly on the center beam rail cars and the flatbed semi-trucks. So basically rail or highway. Here's a schedule that Rob did for us, and it has a very simplified panel count for what we would use for the large office, and we're going to focus on the large office for the supply chains. I did a more thorough analysis of exactly how we're going to lay the panels out on these shipping vehicles and what order we're going to need to take them off in order to construct this office. Also, I looked into how most efficiently we can combine different thicknesses of panels to get them in the least amount of trips. And this is what I wound up with. I wound up with 60 rail car loads and 137 flatbed semi loads. So another thing to keep in mind about this rail is that we can send 10 or more rail cars at a time. So this is actually down to almost 6 trips instead of 60. And because CLT is so easy to build and so quick to construct, it's not unreasonable for us to assume that it would only take a few trips for rail. So when we have the option for rail, we're going to try to use it in this analysis. However, if it's just a short distance, it's not really worth the trouble of moving all the material from truck to rail and then back from rail to truck. So before I show you the maps of the supply chains, I'm going to kind of give you familiarize you with the symbology that we're going to be looking at here. We have a supply chain model. This is probably the most common one that we're going to be looking at. We have the mill is at our location 1. Location 2 is going to be our manufacturing facility where we're going to have a prefabrication occur and pressing. And then site 3 is going to be our build site in South Lake Union. If you see this symbol, which you will, it won't be on the map, it'll be in the analysis, and that's just saying that we can use that site as a transfer station, as a distribution yard or a transfer station. So here we have our first site. This is WA 1, Forks, Washington, and this is Inner 4. It's currently closed, but it's kind of in a state of suspension, so if we have something like CLT to kickstart it, this will be a viable option. We have up here a kind of a legend, and we'll zoom in on this route here, but you can see that we use some of our analysis from the previous presentation as far as how far these logging trucks can go out in 25 miles, 50 miles, and 75 miles. And the region that we're shown here is the National Forest region that we can reach in this distance. And while we can pull from a lot of different sources, this is kind of the one that we're going to focus on. So keep in mind that is also going to be added to the total distance that we're traveling. So if we look at the route here, one of the first problems that kind of comes up with Forks is that we don't have a rail system from the Forks area to the Puget Sound region. And so the only rail that we'll be able to utilize is between Everett and South Lake Union, about 31 miles. So we're going to want to stick to trucks for the most part. And another kind of problem that I saw when I initially did the analysis is this kind of gray region here is they assumed that we would be using the ferry to get this material across, and we might not have that option with freight. I'm not aware of it, but if we do, that will cut about 100 miles off of our trip. So we're looking at option 1 most likely is going to be about 216 total miles, and that is going to equate to about $378. I had a lot of trouble finding estimates for rail. I'm not sure why that is, but unless I wanted to actually ship something with freight, I couldn't get a solid number for that. So if you see this plus sign here, that's just you're gonna factor in the rail trip as well and the money that it would cost to transfer that. So this is just the truck pricing here. So now look at Darrington, Washington, and the first thing to notice about Darrington is that the Hampton lumber mill is very large. I had to change the scale down here from 1,000 feet to 2,000 feet just to fit it into the picture. You'll also notice that it is probably the shortest trip that we have to make. Hampton lumber has the advantage of a rail system that comes straight from the mill, so we can definitely take advantage of that. Look a little closer here. The trucks, if we took a truck the whole way, it would just be 78 total miles, and then we have the option for rail and then truck, which would transfer in the industrial district of Seattle, which I showed you earlier. And in this case, we will probably take the rail just because we don't have to transfer it anywhere from the source. We can send it just down to Seattle straight from the mill, which is really convenient. TWISP is a little interesting. We were kind of suggested the area by a mill owner that said it would be a good place to start a new mill. It also has a lot of national forests to pull from, including Okanagan, Snoqualmie, Baker, Wenatchee, Gifford Pinchot. So there's a lot of options there. I just kind of picked a location right here to use for the analysis, and what's interesting is we do have rail and we do have highway, but we can switch to, let's look at a little closer at this, we can do either Wenatchee or Ellensburg as far as manufacturers go. We have options in both areas. So we're going to go with the Wenatchee trip. It's just a little bit quicker, and I believe for this analysis the truck was the better idea, well, only because I'm not sure if the Pateros, Washington transfer station accommodates lumber. Finally, we have Colville, which is run by the Vaughan brothers, and that's also a very large mill that has rail access straight from the mill. It's also unique in that we have a very large rail system that can transfer in Spokane, Colville, and Seattle. So of course we're going to take advantage of that, especially because it's such a far distance from the other sites. We can increase our efficiency a lot by going that route. So I've included a comparison here at the end, just a quick graph of kind of the rail distance, the highway distance that we would have to travel with our ideal options for each route. You'll notice Colville is certainly the furthest away, but we are taking advantage of that rail. And if you'll remember the numbers, it's 60 trips versus 137, and using multiple rail cars, we can save a significant amount of time. So this is actually a lot less than it looks like. This is true for Darrington as well. I would have put a cost analysis up here, but it wouldn't be relevant really without the rail estimates. So I guess if you can kind of keep in mind the comparison of, well, I guess how efficiently rail would work as opposed to highway, and then I'm hoping some of you viewers are kind of familiar with the rail system and how much that might cost just through experience in the field. So at this point, I'm going to pass it off to John, who's going to do a life cycle analysis.
So far in our project, we've considered CLT to be a very environmentally friendly building material, but up until now, we don't have any numerical values to really back that up. We know that CLT sequesters carbon, and we also know it's a renewable building material, but in order to start to determine just exactly how environmentally friendly or what kind of environmental impact it has, we need to run a life cycle assessment. And what a life cycle assessment is it's the general procedure used to determine material or an object's or a building's total environmental impact. So in general, the life cycle assessment for CLT would begin with material acquisition. So pulling timber from our national forest and then determining what kind of carbon impact, how much energy that would require, and then moving forward to the material process. So what kind of energy would it take to press these CLT panels together? How much impact would the resin used in these CLT panels have? And then moving forward to the transportation aspect side of thing, what kind of general fuel and carbon would it take? Carbon would it produce from the transportation aspect, from taking the lumber from a forest to the mill, to the manufacturing process, to the final installation process of on-site construction. And then we'd look at the installation process. What kind of energy demands, what kind of pollution might that create of the actual installation of CLT in a building. Typically in a life cycle assessment of a building, you would also take a look at the building life use to try and determine how energy efficient the building is. But because we're only looking at the outside shell of our building, we determined that we don't have those numbers. We don't have any heating and cooling systems that are going to be inside these buildings, so we can't develop just how much energy efficient these buildings are going to be used, so we're not going to include that in our life cycle assessment. And then finally, it's the end of life of the CLT panel, and we got to look at if it's being recycled or if it's being put in a landfill, and what kind of carbon impact that has and what kind of energy that might consume. So the general outputs of a life cycle assessment are the global warming potential, the ozone depletion potential, the smog potential, acidification potential, and eutrophication potential. Those are the general results that you would receive from a LCA analysis. But additionally, we determined that we wanted to take a look at the total energy embedment in our CLT models, and that's just another aspect that we took a look at. Some of the assumptions that we used while we were making these LCA analyses were, first off, that for our large office, our mid-rise residential, and our high-rise residential, they're all on concrete podiums. And because of this, we know that if they were built out of a different building material, they would also have concrete podiums. And because they all stay the same depending on the building material, we determined that we didn't want to use the concrete podiums in our analysis. An additional assumption that we made was the fact that because CLT is a new building material, it doesn't have an EPD, which is an environmental product declaration. And because of that, we determined that we needed to use glue laminated timbers EPD because it has a similar procedure in its formation. What an EPD is it's a general tool that an LCA analysis would use to quantify and standardize the amount of carbon, the amount of energy impact that certain material in that system would take up. The general goal of this analysis, of this LCA analysis, that as we move forward and we start to look at buildings with other components in them, like having concrete or steel in our CLT buildings, that we can compare and try and determine what would be the most environmentally friendly options and how that building might compare to our baseline CLT building in an effort to promote and build more environmentally friendly buildings. So now I'm going to hand it over to Errol, and he's going to take a look at some of our more structural analysis.
Hello. I've been working on the past few weeks trying to do some digital methods for structural analysis for the models that we have. This model that you see to my right should look familiar to you. It was created previously by Nicole for massing purposes, that is determining the amount of CLT that would go into building this structure. I wanted to make it work a little harder though, earn its keep. So what I did is in Revit as well, I added loads to each level, dead plus live. Some assumptions that went into this model are that it is a fixed concrete foundation. So the podium that you saw on the previous slide was replaced because we did not want to add that to the analysis. No settlement and no lateral loading at this point. This is a preliminary analysis. We'll delve more into that at a later time. But the dead load for this model was estimated at 45 PSF, and the live load was 40 PSF per residential. And then I brought it into another program created by Autodesk. It's called Robot, and so it gave stress levels in each of the walls. As you can see, the stress increases as the color darkens. So based on that stress, we were able to come up with estimates for what thickness of CLT we would need. So as you can see, the bottom 5 floors, we would recommend 7-ply at this time, and the upper 2 floors we'd recommend a 5-ply. This is preliminary, but it's a good method of doing this because it can take more into consideration as we add complexity to our model. This one was created by Jesse. It is the office building, and so we did a similar thing. Each level we added dead and live load, very similar assumptions, same foundation, no settlement, but notice that the loads have changed a little bit. So for dead load, we estimated at 55 PSF, and for the live load we estimated at 50 per ASCE recommendations. And we brought that in. Now as you can see, the colors are much darker here than they were for the mid-rise multifamily building. It's understandable, it's a much taller building. And as such, it bumped up to a 9-ply for the first 5 floors, and then 7-ply for everything but the upper 2, which we said were a 5-ply. So we're hoping to get more loads applied to this building and work on refining our material properties for this so that we can get more accurate results. If you have any questions, please feel free to contact us, and that's all for this presentation. Thank you very much.